What if we could build a self-driving car that was mathematically proven never to crash? Or a factory robot that was guaranteed 100% to be safe? This isn't science fiction anymore. Today, we're going to take a look at a breakthrough in logic that's making this kind of perfect reliability a very practical reality. So let's dive in. All right, here's our game plan. First, we're going to talk about this synthesis dream, this decades-old quest to build systems that just can't fail. Then, we'll introduce the star of the show, this new logic called LTLBR, and figure out what its superpower is. After that, we'll break down its winning strategy, see where things are headed next, and finally, really understand how it hits that sweet spot between raw power and real-world usefulness. For as long as we've had complex computers, the absolute holy grail for engineers has been something called synthesis. I'm talking about the ability to automatically create flawless systems from the ground up, totally removing the chance for human error in really critical software and hardware. Let's think about it like this. How would you write a recipe for a robot that is so perfect, so airtight, that it can handle any possible situation, and you could guarantee it would never, ever mess up? Well, that question right there is the central challenge of a whole field called reactive synthesis. So, reactive synthesis is basically the engineering behind that dream. You feed a computer a specific list of rules, this is your specification, and it automatically generates the system's brain, or what we call the controller. And this controller follows those rules perfectly, no matter what you throw at it. It's kind of like having an automated programmer that's physically incapable of making a mistake. For a long time, we've used these really powerful languages, like linear temporal logic, or LTL, to write out these rules. LTL is just a way to describe how something should behave over time. Rules like, eventually the landing gear must deploy, or the fire alarm must never go off by accident. But there's always a catch, right? The more powerful and expressive your rulebook is, the harder the computer has to work to build that perfect controller. It gets so computationally expensive that it just becomes way too slow for any practical real-world use. And this is where our story really begins. This classic trade-off, this battle between power and performance, is exactly the problem that a new, breakthrough logic was designed to solve. It's all about getting the best of both worlds. So let's meet LTLBR, which stands for Extended Bounded Response LTL. Now, the really key thing to get here is that this isn't just another logic. It was purpose-built right from the very beginning, with one single goal in mind: to crack that performance problem and make reactive synthesis incredibly efficient. So what does that mean in plain English? It means LTLBR is amazing at handling rules that mix immediate, time-sensitive actions with those broader, always-true conditions. Imagine a robot that must always avoid running into walls, but also has to respond to a user's command within, say, 2 seconds. LTLBR is perfectly tailored to handle exactly that kind of practical, real-world instruction set. So what gives LTLBR this incredible ability? What's its secret sauce? Well, it all comes down to its laser-like focus on one absolutely crucial area: safety. Okay, the superpower of LTLBR is something called safety completeness. Now, a safety property is really just a rule that says something bad should never happen, like the elevator doors should never close on a person. Safety completeness means that LTLBR can express any one of these nothing bad rules just as powerfully as other much more complicated logics. And the clever way it does this is by using what we call past operators, which is basically a fancy way of saying it can look at what's already happened to make sure the system stays on the right path. Here's a great way to think about it. Instead of having this massive general-purpose toolbox that's just slow and clunky to use, LTLBR is like a perfectly organized, specialized kit. It has exactly the right tool for every single safety job you could imagine, but with none of the extra junk you don't need. And that's what makes it so incredibly fast and efficient. So how does this amazing toolbox actually translate into a winning strategy? Let's take a look at the actual process of synthesis with LTLBR. The whole thing is this really elegant 3-step dance. First, you just write your rules using LTLBR. Second, the system automatically builds something called a deterministic automaton. Think of it as a super detailed flowchart that maps out every single possible state the system could ever be in. And finally, it boils the whole problem down to solving a safety game on that flowchart, where the only goal is to find a winning path that never lands on a bad state. And it turns out, computers are ridiculously good at solving that kind of game. And get this isn't just some happy accident. The very structure of the LTLBR language, with its 4 distinct levels, was intentionally designed to map perfectly onto this synthesis algorithm. Each layer of the logic feeds directly into a specific step of the process, which creates this incredibly smooth, streamlined pipeline from your initial rule all the way to the final working system.
But the story doesn't stop there. LTLEBR has proven to be such a solid foundation that it's now being used as a launchpad to build even more powerful tools.
And this is where new logics like GEBR come into play. It basically takes the super efficient core of LTEBR and bolts on more sophisticated features, things like making assumptions about the environment or adding guarantees about the system's long-term behavior. This lets you specify rules that go way beyond just simple safety, but you still get to use the fast, safety-based algorithms that made the original so effective in the first place.
Okay, so let's bring this all together. What's the big takeaway from all of this?
This comparison table really says it all. When it comes to safety properties, LTLEBR has all the expressive power you need. It's on par with the more general methods. But where it wins, and where it wins big, is in the method. By focusing on these simpler, highly efficient safety games, it delivers an algorithm that isn't just faster, it's optimal. In practical, real-world tests, it just flat-out outperforms the other approaches. So the bottom line is this. LTLBR finds that perfect sweet spot. It doesn't sacrifice any of the power you need to define really complex safety rules, but it packages that power in a way that makes automatic synthesis fast, practical, and actually usable. It takes that old dream of building provably correct systems and brings it a giant leap closer to our everyday reality. And that leaves us with a really fascinating question to think about. Now that we have tools like LTLBR that are making it easier than ever to build systems we can truly mathematically trust, what kind of future could we design? What huge problems could we solve when the phrase, failure is not an option, stops being a motto and starts being a mathematical certainty?